All right, let's go ahead and get started. Good morning, everyone, and hello. Welcome to Unlocking Success and Building Jetting Solutions. My name is Dennis Barnum with Dendrite, and I am happy to turn this over to our CEO, Harshal. Take it away, Harshal.
Thank you, Dennis. See if I can share my screen. All right, so as Dennis mentioned, welcome to the webinar. I'm going to be just doing the kind of the opening intro remarks. So the first thing I'd like to do is essentially just introduce our expert panel. We have a whole host of experts here today who probably honestly quite too humble to really talk about themselves. So I'll be less humble for them. We have Mr. Dan Brunermer. Dan is probably one of the most knowledgeable folks I know. When you consider jetting, he has 20 plus years of experience. We then have Dr. Kate Black, who has a expertise in material science and chemistry. We have Matt Pullen from Meteor. They're a leading supplier of key solutions for jetting systems. And then finally, we have Dr. Steve Walton, who is Dendrite's head product, formerly Blue Origin, who will be explaining the software component of things. So maybe to kind of just level set some stuff here, what is the purpose of this webinar? The purpose primarily is education, right? Everyone who's attending here is probably trying to build a jetting solution of some kind, shape, or form. And it is the goal of this webinar to help people overcome the traditionally higher failure rates associated with trying to build these solutions. There's a ton of things that go into making this, and the folks who are going to be talking today have quite a bit of experience with essentially every aspect of what it takes to go make a jetting solution. The next key reason for this is to honestly build a community to promote overall success. I genuinely believe that most of the people who are actually attending here today are not necessarily actually competitive because everyone is trying to go and perform in a very specific niche. And so rather than necessarily keeping things from each other, it might actually be beneficial to actually build a community and help each other. Because again, building some of these sophisticated solutions is that difficult. And then finally, just to kind of add to this, I want to make it known that there will be a Q&A at the very end. Please feel free to use the chat feature to ask any of your questions. Please feel free to ask difficult questions. I promise you, everyone on the panel is more than capable of answering them. And all Q&A questions will be addressed at the end of the presentation, not after each speaker. So to just kind of get things moving and shaking, I wanted to kind of just take a quick poll from the audience. What kind of best describes you from a discipline or a background standpoint? Do you have a background in hardware? Are you a mechanical person? Or do you have a background in software? Or do you have a background in materials chemistry or other? Please take a moment to fill out the poll. This will kind of help us tailor the content for the webinar. We'll give the poll maybe another 30 seconds. All right, Dennis, can you stop the poll? Or maybe I can just continue talking. So, in summary, what is this talk going to be about? And what's kind of the theme of the talk? The theme is the whole is greater than the sum of the parts. We specifically asked this poll, right? And as expected, the overwhelming majority of folks on the call either have a hardware or a materials chemistry background. Right? The reason for uh, this webinar is because in order to be successful in this field, you must be successful in the hardware, the software, and the materials. This is primarily because, well, the software tells the hardware when to do stuff. The software is important for telling the materials where they need to happen. And then, of course, the hardware and the materials need to work in concert to figure out what needs to happen. And all of these things need to happen together, right? All of manufacturing at the end of the day is about where you do what and when. That's the only way that you can actually make something sophisticated. Moreover, it's important to acknowledge that this is a extremely difficult and multidisciplinary field. So congratulations to everyone on the call for picking an extremely difficult field to work in. And it has often been our experience that when someone starts trying to build a jetting solution, they're usually leaning heavy into either the hardware or the materials. And then they end up kind of making the other two fields essentially kind of second hand. And the idea here is that if you truly want to be successful, you actually need to consider all three things at once. This is what kind of makes this kind of difficult. So without further ado, I'm going to introduce Dan. He is going to talk about what it takes to go make good decisions. I can say that calling Dan a subject matter expert is honestly a gross understatement. He has 20 years of making these decisions, and he's about to give you an overview of how kind of essentially all of this fits together. So with that, I would like to introduce Dan.
Well, thank you, Harshal. I assume I'm sharing my screen. So, hey, thanks again for that introduction, and thank you, everybody, for attending today, this little chat about making good decisions. As Harshal says, I'm a 20-year vet here of binder jetting, getting my start in 2001, making the first of its kind drop-on-demand direct metal printing machine. And boy, I tell you, that was a really tough 6 or 7 years to get that guy to work. But hopefully after today, I'll help you make some really good decisions, and you'll have a little bit more success getting off the ground. So, as Harshal says, we are going to be focusing on, three essential aspects here. That is to say, the software that is to say, actually, the materials first. We're going to start by talking about materials and how you pick them and what you need them to do. We're also going to talk about these printhead controllers and printheads themselves, and what kind of magic you can unlock if you have the right kind of modules with the right kind of hardware driving them. And then, of course, this whole thing, the reason why the software is the big part here, it's as Harshal says, when it comes to additive manufacturing, it's almost 100% software. Your software is kind of what everything's built on, from your CAD to your, from your CAD design, simulation, all those programming, all that stuff. It's all basically software. And you could say even that the Industrial 4.0 revolution, it is software. But and I'm pretty sure that this is a well-educated crowd, so I'm really not going to get into what binder jetting is, but we all kind of know, kind of like what we have on the right here. There's this idea of a voxel field that we need to fill in with a binder, a powder, a jetted material, whatever. We build that on stack. We're going to be talking a lot about printheads and printhead controllers, not so much about recoders and layer creation software. Those are almost pure hardware. They have parameters, but they're a little bit outside the discussion for today. But so before I get into all this technical details, the first thing I want to address is, why are we doing this? What am I trying to do in my manufacturing enterprise with binder jetting? What are my goals? What am I looking to do? And we all kind of know that we're all trying to make the best possible product, and we're trying to make the best possible product, balanced across a complex set of axes. I've only chosen 5. You can choose whatever axes, however you want to measure your products and optimizations. But, the idea here is that we're trying to add a technology that's going to boost us somehow. We all know, all forms of additive are very flexible. We're starting to learn how all forms of additive help with sustainability. And we're really starting to see with these binder jetting companies some very productive, high quality systems. And, the reason why you're bringing this in is because you're trying to make all of these axes better, and you've got to kind of consider them all while you're making your machine planning decisions. But as I say, I'm going to start with materials, and I'm going to try not to take too much of Dr. Black's fire here, just to say that, the jetted materials, the way this all works is you have this material that you're jetting, right? And you're generally jetting it into a powder. And you have this thing that we've called the printhead and its controller, the software around it. But at the end of the day, what it does is it makes a droplet, right? Like it makes a droplet binder, it makes a droplet of UV cure, it makes a droplet of something that interacts with the substrate underneath it. And both of those materials are important. Your binder and your substrate have to work together in any printer. I mean, a 2D paper printer, it's the same thing. But you really have to start there in these applications because, what you need is going to drive a whole lot of other decisions about things like printheads and software and whatnot. And I'm going to say the only way that you can really get these benefits of binder jetting and some of these new amazing materials is you have to invert your thinking about how you design your products. You know, you can't just swap one part for another and think binder jet's going to make it better. That isn't how it works. You've got to reevaluate starting from function. How does this part have to perform in the environment it's in? You know, we often think about, we talk about form, fit, function, and we put function last as if somehow that's like not the most important part of your thing. But you've got to put that function first if you're going to take advantage of some of these great new design tools. If you want to get into generative design, let's say, you've got to know more about your part's function and the material properties that can come about if you're going to truly get optimization. And every consultant will tell every customer this. You have to start with function. You have to reevaluate. Don't start by thinking about materials and their manufacturing processes. What you need are materials properties. And just to kind of put a little bit of color into it, you know, when we talk about jetted materials and substrates in terms of jetting materials, the reason why you want to keep some of your options open on printheads is because maybe you want to use unique carrier fluids. Maybe you've got some special modifiers or some special active ingredients, and you need these to be both compatible with your jetting module printheads and your fluid delivery system and everything else in your machine. And then, of course, the substrates are similar. If you're doing material jetting, of course, you've got a base and you've maybe printed some supports you're printing on top of. For where I'm in, my expertise is obviously in binder jetting, where this substrate's a powder, and preparing that layer is kind of critical. You've got to have a material that can be made into a layer is probably the proper way to put that. Okay, so now let's move on here and start with a little introduction to what these printheads are and what I mean when I say a jetting module and the control electronics and how this all works. As I say, we're not really going to talk too much about recoders other than to say that it is an important part of your machine, and having the substrate in the right state to receive the jetted material is a very critical thing. But we're going to focus more up here next. Okay, as I say, and I'm going to try not to take too much of Matthew's fire either, but I just want to talk a little bit about, you know, what these ink jetting modules and about your control electronics. So, you know, essentially, an ink jetting module is like this incredible little micro pump. It's almost like a diaphragm pump. You can kind of think of it that way. But what's unique about it is that the diaphragm is, you know, it's designed for almost ultrasonic operation, right? It's a piezo. So as you apply voltages, you create, you know, true mechanical distortions. And what if you pick the right controllers, you basically have the ability to do all these different analog waveforms, which is basically you can think of as the direct control of the piezo unit itself. But you also have to have all that in total synchronization with your data streams. And things like your data channels and your data lengths and all these things are going to kind of dictate what your maximum firing frequencies can be, what your maximum run speeds are going to be. So having a good set of electronics that gives you lots of options is a really important part of this, especially when you're first starting out in your particular process. And okay, you know, so this is the software slide. And like I say, when it comes to Industry 4.0, there is a ton of software here, isn't there? You know, we can revisit that product lifecycle and we see that, you know, surrounding it is just all kinds of stuff, right? Like, I mean, we talk about the 4 levels of manufacturing enterprise control, right? Like when we say the executive, operations, intelligence, devices, and then just the basic physics where we lose control, right? That's what we try to simulate. And today, you know, we're essentially going to be talking about this little part of it, but realize that when you're designing your software, you need to be able to have a back end, an engine of some kind that lets you talk not only to your machine and make images, but you've got to have back end support. You've got to have support for operations. You've got to have executive level support. You've got to be able to have your machine be more than just a printer. You know, if you're going to have an Industry 4.0 solution, you've got to be thinking about this entire solution. And remember that at the end of the day, it's all about this, right? It's all about getting those orders, making quotes, delivering parts, and getting paid. That's why we're doing it. And, just to bring it up, we always talk about there's 3 digital threads that make up the digital fabric. The thread of your machine, or I mean, the thread of the process, the 20-year part, and then of course your entire manufacturing operation. So you want to make sure that you have a good engine and back end that can provide all those interfaces. But as I say, I'm just going to break down a tiny little bit about what we mean here whenever we say, oh yeah, prep the files and print them. Great. There's a whole lot that goes on in the back end there, right? We already know, any of us in additive, we know things like you've got to do bed layouts, maybe support structure, shrinkage, compensation for binder jetting, different sintering things. So, when we're talking about preparing all those files, you have like that basic set, right, of things you do. But then you have to, in the last step there, is voxelize all that data. And when we're talking about voxelization, what we literally mean is, when we talk about slices, well, now in addition to slices, we're talking about planar slices in 3D that make these uniform, voxels, as we call them. And it's, it really is a volumetric pixel. And whenever we talk about printing the job, we kind of make it simple, right? Like we just say, hey, set up your machine, spread a layer of powder, print the image, give it some heat, do that over and over. But there's a whole lot that goes on behind the scenes there. From loading, so you've created this voxelization, right? And somehow you're encoding in this 2D image stack what it is that you want to come out. So what I'm kind of showing on the right here is the kind of super simple application that I basically was solving back in 2001, where, we didn't really have a whole lot of options. There was no dendrite, there was no meteor inkjet, there was no, nothing. So it was very new. And the best I could do in those days was just basically come up with binary representations, either one drop or no drop. And that was it. That was, and frankly, that was hard enough. But today, with these new voxelization tools and these new print engines, we can actually encode in this map more than just, on and off. Maybe we want to have, gray scales, or maybe we have 2 different materials. Maybe you're doing material jetting with 6 colors, so you've got to embed all this information in the voxel map itself, but then you have to have a meaningful way to extract it. And that's what we mean by this RIP here. It's called a raster image processor. And what that actually does now is it reinterprets this voxel data, turns it into those data and waveform descriptions that I was talking about earlier, puts it all into a neat little buffer, and then you execute your print press. You synchronize your axes, all those kinds of things, but then you do it. And that is a ton of software just to get from a model file to some kind of data stream that's compatible with the jetting module you're using, and you're trying to fire it with all these complicated waveforms. And it's a whole new world now than it was for me. That's one of the things that I'm most excited to see actually in the future, is how these much, much better systems get implemented and used. And so that kind of brings me to, B-Jetting LLC. And when James and I were talking about whether or not we would do a platform, we just had so many customers coming up to us who wanted to get into binder jetting, but they just couldn't find a jumping off point where they felt comfortable getting in. There's lots of solutions out there for high production, super high quality machines. They just happen to be kind of big and expensive. And what James and I wanted to do is come out with something a little bit different. We wanted to really maximize that flexibility. We wanted to really minimize the costs. And one of the things that I really wanted was just something really compact. I always wanted a machine where I could just keep all my work in front of me and change things however I saw fit. So what we came up with was the Researcher platform that's based on an open architecture, open software, open solution, and where, we have these slots, we call them, pretty fancy name, I know, but the slot system is what lets you put in a different module. So if you wanted a ZAR, you could have a ZAR with ZAR Electronics, plug that in. There's a software backend you can tie into. You want to use Fuji, you want to use Seiko, it doesn't matter. All of those backends are supported on this platform because it's a totally open platform. And when it's powered by dendrite and meteorite, it can let you do all those cool things that I was just talking about. And so we're pretty happy with this system. And but again, it's all about making the tool that lets you find what your most productive machine is going to be. And so here's my summary slide. I mean, this is the big bad world of binder jetting. And you've got it when you've made this decision, whether you're going to design your own machine or whether you're going to buy a machine, you know, it's important that you're asking the right questions so that you can make good decisions. And as I say, this is just kind of a big overview of where everything about your process has to fit in and all the different kind of software you need. And being able to cut out that part of voxelization to rasterization to printing data, boy, I'm very happy to have partners to work with us on these days, because it's the future is pretty bright and amazing. Okay, and with that, I just want to say thank you again. Thank you to everyone for coming. Thank you, Dendrite, for setting this up. And it is now my pleasure to introduce Dr. Kate Black, Professor of Manufacturing at the University of Liverpool and co-founder of Meta Additive. Take it away, Kate.
Thanks, Dave. Let me share my screen. So that should be sharing now. So hello, everybody. I'm Kate Black. I'm a professor of manufacturing here at the University of Liverpool. And I'm the co-founder and CTO of Meta Additive. So you've just heard from Dan a fantastic holistic view there of what's needed for successful jetting processes. But I'm going to talk to you a little bit now more about the material side and how we might unlock the true potential, in this case, binder jet printing. So it's predominantly focused on binder jet systems. So I know a lot of you in the audience are probably binder jet experts, but I thought I'd give a brief overview of the current system, because that really exposes some of the difficulties that we have and some of the issues that you might face when producing a successful jetting system. So as it stands, most current binder jet printing systems have either 4 or 5 step processes. So we've got the powder bed, and that has an added benefit of being able to be composed for a range of materials, so polymers, metals, and ceramics. But it's then conventional for these powders to be bound by a polymeric glue, where the sole purpose of that binder is to just do that very thing, that bind the powder together. But it's this stage in the process which I think represents an area which is rife for investigation and therefore improvement. So once these parts are bound, they then have to be debound, and usually that's outside of a print chamber. And this can be quite a lengthy process step, but you need to be careful, because if this is not done properly, then we can start to introduce contaminants into the resulting printed component. We then got this 4th step. This is another post-processing step, and this is sintering. And we need this sintering step because it's required to consolidate the component before it's ready for its intended use. And it's the debind step and the sintering step which I think causes most of the problems that we see with binder jet. So part density, part shrinkage, and they're all limiting its use of binder jet in a whole host of applications. Yes, we can add a 5th step, which you see in this schematic, which helps to, well, it infiltrates first, so that improves part density. But that doesn't work for a lot of material systems and for a lot of applications that people have. So we're left with these disadvantages of having low density. So it can be as low as 60% for green parts, so as you've taken the part off. And this low density then causes problems further along down the line in the form of high shrinkage rates. And we're seeing some wonderful software that's coming out that we can start to model to mitigate the risk of shrinkage and distortion after sintering. But as the the parts become more complex in geometry or larger in size, then it becomes more challenging to try and mitigate that. So we see these several processing steps, the debind and the sintering and infiltration, and these can often be very lengthy steps. So we need to eradicate these if we're starting to see binder jet systems for mass production, looking at the debind step and making that more rigorous so that we can do automated debinding steps, a stronger green part strength, so that we can do mass production of parts. So this slide is entitled Materials are Key, because I would, as a material scientist, really think that materials are the answer and they are key. And if we look at binders in existing binder jet systems, that causes most of binder jet's current problems. But in my opinion, it also simultaneously holds the key to unlocking its true potential. We live in a world where we're facing a whole host of complex challenges, such as energy shortages, climate change, global pandemics, and the world needs the manufacturing sector to come up with smart manufacturing solutions to tackle these challenges. But if we're to do this, we need to start putting the materials in those processes at the forefront. It doesn't matter what we do or manufacture, materials are the building blocks of every structure and system in the world. And if we look at additive manufacturing systems, but in particular binder jet printing, what we're currently doing is we're taking high quality material, putting a lot of time, energy and money into those processes and turning them into powder, which then we essentially glue back together again, albeit being with complex geometries. And if we're to provide the world with proper smart manufacturing solutions, then we need to start putting the materials first so that we can have the benefits of not just complex geometries, but also bespoke material properties. And that's where we'll start to see the magic really happening. So how do we manipulate materials at submicron scale to give us both the bespoke geometries and the bespoke material properties that we need? Well, I believe that binder jet is that technology that could really live up to a lot of the hype that we have created and heard over the last couple of decades in the additive manufacturing community. And why do I think that? Well, it's got potential flexibility in both binder and powder. And today we're not going to focus on the powder, but it's got that flexibility for both of those to be modified and changed. And that will move us further towards volume-ready production, but in particular, help us to realize true multi-materials in these printed components. So to do this, we need to start looking and thinking about binders differently. And in fact, not just see them as simply a binder that binds powder together, but a step in that printing process where we could enable materials with bespoke functionality. Imagine if those binders had embedded sintering agents, green strength enhancers, debind mitigators, and microstructure modifiers. But to unlock some of that potential, we need the software to support these more complex material systems. And we also need the print heads and the drive electronics, which can efficiently and effectively deliver those more complex materials where we want. And you're going to hear more of that from Steve and Matt shortly. But if we're to build successful jetting solutions, we need to first start with materials. So the next couple of slides, I'm going to cover some material approaches that myself and my team at Liverpool University have been working on, and some of which went on to form the basis of the spin-out company, Meta Additive. So the process which we developed at Liverpool uses binders that don't just see the binder as a binder. It doesn't just hold polymers. In fact, many of our applications, it has no polymers at all. In fact, we have a jetting solution that has functional fluid, and this acts as a binder and simultaneously as an infiltrator. So the binders are reactive solutions, and hopefully you see here in this schematic how they all build up and what role they play in that system. So the powder can be consist of regular AM powders, which we're familiar with, but then they're bound together by jetting a functional reactive binder onto the powder. And this binder is molecularly designed so that it chemically reacts in a certain way with a certain powder. and that forms either a metallic or a ceramic conformal coating. In this case here, you see this is just copper for an example. The micron particles then held within that binder, in that solution, fill in some of the interstices, some of those pores in the powder bed, and they can be up to a micron in size, depending on what print head you use, and that's why print heads are really important. We've then got the nanoparticles. They also fill in some of that porosity, but they can act as sintering agents and also microstructure agent and modify the microstructure of the resulting part that you've printed. We've found that we can control the size of the grains in our copper printed parts just by modifying the size and the quantities of the particles in the binder. So those reactive solutions of the components can be tailored for conformal coatings of metal and ceramic. So you're infiltrating and binding with real build material and not sacrificial binders, which is what you normally see in conventional binder jet systems. So because of these types of binders, we're simultaneously infiltrating the powder bed and we're binding, we can remove some of those process steps. So remember the previous slide where we saw that 4 or 5 step process, we're now reducing that to a 3-step process. That means reducing manufacturing time, but also we find that we can often lower the processing temperature at which we need to heat treat, as well as shorten that time required for sintering. But then, due to the additional components that we're adding to that binder, it enables us much greater flexibility as to what materials they could be. In this particular case, we see on the slide here, we're using copper, but imagine if that powder bed was one material, the microparticles held within the binder are another, the nanoparticles are another, and then the reactive organometallic is another. We can start to see how these would be transferable to different material systems. But also we could start to see for the very first time graded material structures or graded multifunctionality across that 3D geometry. So we've mitigated the risk of porosity or high porosity in parts. We've mitigated the risk of shrinkage because you're infiltrating with build material. But then you've got that added benefit of being able to transfer to a whole host of different material systems and be able to control the functionality. You heard Dan talk about how important it is about functionality of materials. It's not just the materials, it's what function do they allow us to play in the overall printed part. So with this approach, we have much greater flexibility. I also want to talk about a more complex material system. So here's one from a completely different area. And this is an example of some work that I did with a company called Colourforge, who produce bespoke 3D printed cosmetics. So here, they don't only just print the cosmetics, they also print the container in the same system. And we can be using up to 6 different material print channels in the process. And these are now quite complex materials, all need to be placed in quite complex areas. So you've got bespoke volume-ready production, but also multi-material systems at the same time. So we've talked about the machines, we've talked about the materials, but now this requires careful software that enables us to accurately tell the print head where to place the different materials. But also the process design files, so the input files, they're no longer your CAD and then STL files. These have geometry, but also need to say, where does the material need to be in that geometry? How do we grade through materials across the 3D space? Or even grade dosing rates to enable graded microstructure and density across a 3D space. And this is where software comes in, being able to enhance functionality. And you're going to hear from Dendrite how they've been helping solve these issues. So input files are becoming much more complex and there's a greater need for greater control. Controlling where that droplet volume and type at specific locations go. And that will allow us to have greater material functionality. But we've got the machines, we've got the materials, we've got the software, but we also need robust print heads and electronics. And so you're going to hear from Meteor, from Matt, and he's going to talk to you about products such as MetPrint. This helps deliver those materials at the quantities and the volumes needed. but it'll support you not only through a prototype environment, but right through to production. And I think that's really key. If we're to start seeing more jetting solutions coming from the academic arena, going into the industrial arena, then we need software and hardware and electronics that will allow us to take us from that prototype phase into the industrial scale-up phase. So where does that leave us for the future of binder jet? Well, it's really important, and this is why hopefully you'll see today that it's not just one area or aspect of that jetting solution. It's a whole ecosystem. So we've talked about raw materials. We've done some on the machines. We're going to hear from Matt shortly about print heads and electronics. We don't talk about characterization today, but that's also really important in that ecosystem and that a successful jetting solution. But then it's all tied together with the software. So I'm going to hand you over to Steve, who's going to talk to you about what Dendrite have been doing to tackle these issues.
Thank you, Kate. All right, thanks for properly motivating some of the multi-material and functionally graded material opportunities that we have with binder jetting. Today, I'm going to be talking about some of the software tools that are available along the way for use by someone developing either a new material, a new process, or a new application, a new functional application, as Dan mentioned earlier. So what is Meteorite? Meteorite's a tool, software tool that's been a collaboration between Dendrite and Meteor. I'll do a demo of that here in a few minutes. But again, this is really set up to enable new applications with new materials and processes, as Kate was mentioning. So what this tool can do is configure multiple registered image stacks with different bit levels, different image sizes to get started with that early process development, bringing together the software, the materials, and the hardware. So let me go ahead and bring up the Meteorite software here. And we'll start by configuring the print head here. So you can see this build volume. This is a cubic build volume that's defined in the Meteorite tool as driven by the actual physical attributes of the print head. So we have nozzle count, nozzle pitch. If we have multiple rows of nozzles, we can choose to interlace those or not. We also can set up the DPI in the print head travel direction. So you can see with these configurations, we're going to be generating an 800 by 1200 pixel image of this 50.8 millimeter build volume. So I'll just go ahead and apply those settings and import a part. So I'll import, in this case, this part. I'll select it. We'll move it to the center of the build plate, raise it up. And in this case, we'll just quickly slice this and show what the output images look like. In this case, we're just doing a binary image stack, but you can see we have this now stretched image that accounts for the non-square pixels given the print head configuration that we had set up. Go ahead and reset this build environment. And instead of adjusting the printer settings, we're just going to import, we'll import the same file again. Again, center it. It up. But now we're going to look at some of the additional controls in this tool to provide some of the multi-material exploration. Or just graded material exploration. So in this case, we're going to create a shell on this part. We're going to make it an inward shell of a thickness of 0.4 millimeters. Apply this. Now we'll specify gray levels of the different types of geometry that now exist in the build. So after we've created the shell, we have the resultant shell, we have a core inside the shell, and we have the void or the area around the part itself. And so what we can do is for each of these different geometry types, we can specify a material or color plane that we want to use, specify the bit depth. And in this case, we'll just do the shell and the core on the first material, and we'll specify an additional material for the void and pick a different color here. So we'll apply that and go ahead and slice this. And so in this case, since we have selected both the core and the shell to be in the same material, they will be in the same resultant image. And then the other material that was assigned to the void will result in a different image tag. So let's actually go back here. So we can see that the shell, this offset inward shell, was created, and on the first material. And if we look at the other material here, we actually can now see that void with its specified bit depth. Now, again, these images are just used as a means to communicate where these different materials need to be placed in the build volume by the electronics that Matt will talk about in a few minutes. But we also have additional controls beyond these using some of the other dendrite tools that I'll talk about here shortly. All right, so I guess one other additional thing to note is the naming convention here. We have a similar slice stack to what I just generated. We have the material or color plane number along with the meteorite slice count. So in addition to just that shelling or that 2D shelling or 3D shelling operation that we just executed using meteorite, dendrite offers many other segmentation APIs or many other ways to cut up a part throughout its volume for the purposes of applying different material parameters or different process parameters. In addition to the shell or the sign distance field, we also have downskins that we can create. We also can create upskins. And then we also can propagate volumes into a part from regions. So a region could be derived from some CAD metadata, such as a color on a surface. It also could be derived from manually selecting a surface, or through an angle overhang filter as examples. So a result of that process being applied is shown here, where we have the entire part core as shown in this dark gray. We have a normal sign distance field shell here being created. And then we have a downskin in the blue. And then we have this yellow volume. And this yellow volume was created from actually a region and then propagating that region into the volume of the part. So you can see in this inset on the left, we have this region identified as a 30 to 45 degree angle filter. So after we use the angle query tools to create this region, we then propagated that surface into the part, creating a volume. And in this case, that volume had the highest priority in yellow, which is why you see it in this multi-section view of the part. And so in this horizontal plane would be an image that could then be sent to the machine to actually deposit different materials or different process parameters. Additionally, this image could be stretched or ripped to different color planes or image swaths or other controls that might be necessary for the jetting process. So beyond that simple view that I just showed, there's also the opportunity to start segmenting parts up into using much more sophisticated means. This is an example that shows 4 upskin fields, 4 downskin or segments, 4 downskins, and 4 sign distance field in addition to the core. And this is just a single slice through that geometry, and you can see all of the different colors here. Again, these could be ripped to individual images or just sent as one. In this case, we're showing colors, but of course we could also use grayscale or monochrome images if we're just varying one color channel. So how do we kind of get started using these tools? So this is a very complicated example, but we could make a somewhat simpler example. In this case, I will run a script here that brings up some of the other dendrite tools and will show the segmentation on a part given some identified colors on the surface of the part. In this case, these colors are used to derive regions, and those regions we create volumes within the part from, or segments. So you can see we have these different colors inside the volume of the part that have been created. You can actually scroll through additional section planes. You can see here, we have the gray core volume and the red section plane showing the volume here that was derived from that region. So again, on the 2D plane, we have a slice like this that now has the different parameters distributed in space on a 2D plane. So that's an example of how that could be applied. But as you're doing a design study to develop the actual process parameters and explore the parameter space, we need some more rational tools to be able to do that easily. And so that can be done using several of the other Dendrite build control APIs. In this case, I'll show an example that just uses the build volume, the part size, and iterates through a number of different parameters to explore the design space. So, and also in this example, we're connecting to a database. Many of the parameters, the actual parameter bounds are being defined in a database, but we are programmatically varying the parameters within that space in the context of a Python script and the Dendrite APIs here. So in this case, we are generating an array of 16 parts. Each of those parts have 6 additional areas where we're looking at different parameters. And this layout is being generated in real time on my machine. And then we could slice this to the image stacks for a multi-material application to be consumed with the Meteorite tools, or the Meteor tools, excuse me. So in addition to those kind of build control APIs that use part measurement, part placement explicitly, and building logic to place those, in this case via Python, we offer additional controls that are very relevant to both to many binder jetting applications, including 2D and 3D nesting. So our 2D nesting APIs include a concept of constraints on a per part basis, and additionally constraints on a per nest volume basis, and that all fits within a build. So on a per part basis, we can specify whether a part should be locked, like fixed in space, its rotation be locked, or allowed angular rotations per part, whether it's an angle increment or a plus or minus degree of rotation. Those can be, again, specified per part. And then on a per nest volume basis, we can specify parameters for spacing between parts, spacing a margin, or define a margin against the allowable nest volume. And that nest volume can actually be a subset of the entire build volume. We also can explore convex space or holes within parts for 2D nesting. Similarly, for 3D nesting, we have control first specified on a per part basis, either locking a part in space, and which would enable you to nest additional parts around the part that is locked. We also can lock all degrees of freedom, or any degrees of freedom, to just make sure the part translates. And then also we can specify any allowable vectors to rotate the part around. And then around those vectors of rotation, we can specify the increments and bounds to explore during the nesting algorithms. And then when we actually move up to the per nest controls, we again consider margin against individual parts and margin against the defined nest volume, which again can be a sub-volume within the entire build. So just showing some of the additional controls that we have to both explore the different opportunities with the multi-material or functionally graded materials with the segmentation approach, and then how those can be developed using the APIs for build layout and database integration. And then further, how that we can kind of start with the reporting aspect of that, because we have additional metadata that can be used to talk to those process control databases as you really get into that process development. But tying it back to Meteorite, right? So this tool is really set up, again, with Meteor to get new applications up and running. So again, working around the parameters and constraints of a print head and of the different kind of controls you might want in a multi-material application. Those are exposed. In this case, we're setting up a build with 5 different parts with the image bit depth of 4. Again, different shell, core, and void colors. In this case, we're showing 3 different material assignments for each of those different types of geometry. And here's a slice just showing the resulting image for material or color plane 1, right, where we're varying across this build the shell thickness, with the thinnest shell on the left and the thickest shell on the right. And the resulting images are shown here for the same slice that I showed previously, for the 3 different color planes with the shell, core, and void here. So I guess with that, I'll pass it over to Matt to talk more about how this data is consumed on the Meteor side and all the additional controls that are there for mapping this image data to printhead control data on the controller.
Thanks, Steve. This is coming through now. So yeah, thanks to Dendrite for hosting, for Dan, Kate, and Steve for setting the scene on where Meteor fits in this workflow for driving inkjet printheads in additive manufacturing, whether that's binder jetting, material jetting, whatever the terminology is for drop-on-demand deposition of materials in this way. And the consistent theme is of the quality of preparation of input and output, whether that's the mechatronics in the bejetting machine, the material development from Kate, and the way we convert from voxel to pixel to generate this inputs into Meteor's print engine for coordination of this data. So Meteor has a wonderful position of being a preferred partner with these 9 printhead manufacturers. That means we support over 75 models of printhead from these manufacturers. So that gives us a whole range of capabilities to explore in looking at inkjet and additive. There are some large drop 50 DPI printheads through to small drop 1200 DPI printheads oriented towards high-speed single-pass traditional print and competing with analog there. In turn, all those properties of printhead, whether it's specsmanship in terms of frequency of operation, resolution, materials compatibility, and so on, have an impact in how you drive them, how we design our electronics architecture, and what materials you can put inside. So we work on a common architecture where we have a print controller, and that's the interface to the machine, taking that encoder signal in, converting it to print clocks out, distributing that data down to tens of thousands of nozzles in a printhead array, across a range of multiple fluids. Traditionally that's color planes, and now that's expanding into fluids rather than inks. So that's designed to fully support these capabilities of every printhead, and the hardware and the software that drives it are oriented towards ever demanding applications for using these contactless print modes. To follow on from what Steve was showing in the how Meteorite has been developed by Dendrite to take our build box and therefore manage the imposition of a part within it, to then manage the materials within it that are split out into color planes or material planes, and sliced based on the expected output of our printheads, both in the resolution in X and Y, one being fixed by the nozzle pitch, the other being up to the mechatronics of the machine to determine the direction of print. When we put that layer stack that Steve showed as a series of sliced data in our print engine, we overlay those so we can see each of those materials side by side. In this case, they're represented by our traditional CMYK representation of, in this case, where we're printing our material, where we're printing a separate material in a shell or a release agent around our printed part. And within that, if it's not in binary, it's starting to utilize these grayscaling effects, shelling and core techniques to put different drop distributions down, or different materials selectively to achieve these structural properties. Whether you want low shrinkage in the shelling, but you want to maintain a low density of parts, so you use a different infill regime using different droplets, different materials, and different matrices to create the internal structures of a part. So that's where Meteorite is feeding Meteor with quality data of conversion of voxel to pixel, and that conversion allows us to implement different printing regimes developed in decades of experience in the 2D space, to treat each of these layers as an image or document, where we can apply printing regimes, grayscale, screening, compensation for missing and deviating nozzles, to make sure that in a 3D print process you sustain reliability, and most importantly yield. You don't have any voids or weaknesses. When we continue to talk about selecting print heads for binder or binder jetting or 3D printing applications, we start to our customers are pushing the bounds of what they want to do in both directions. We have customers using 1200 DPI 3 picoliter size print heads working at the lower end of 5 centipoise fluid, so they're relatively low viscosity. That means you have a native inability to suspend large particles and high densities of fluid. So you use resolution and productivity, speed of print, in order to build those print regimes up. At the other end, working with the printhead manufacturers, the materials developers are able to push the envelope of what's physically possible to print. So now, with using recirculating printheads with high shear modes of operation, we can generate enough pressure within the printhead to jet fluids of up to 100 centipoise. With that high viscosity capability, allows the ability to suspend larger particle sizes to achieve those material sciences advances that Kate's covered, to mix micron size and nano size distributions of additives to your jetting fluid, to interact with the substrate or the powder bed to achieve new physical properties in printed parts, whether that's green strength or final strength in parts. And again, up the solid loading by having these heads with high flow recirculation. We can push those boundaries. So some of those are proprietary figures that are only available in a few heads from ZAR, and anywhere in the middle there are print heads from other manufacturers that achieve those properties. So ultimately, with the inkjet system, we're trying to deposit material at exactly the right time. And when we jet that drop, we want it to fire from the printhead cleanly, nice and straight, and fast enough to register and land into our bed where we want it. And obviously, finding a trade-off between the mechanical handling of how close we can put that printhead to the powder bed means a compromise between velocity and quality of the droplets you're generating in the head. When we talk about generating these droplets, we talk about applying a waveform to the head, something that Dan covered and Steve covered. So these are temporary pressure pulses we generate in order to eject material from the nozzle. So it's a voltage and time signal to create a negative pressure as we fill a channel, and a positive pressure to eject a droplet that's then arrested to detach that droplet and push it away from the printhead. And how these waveforms are generated will depend on the printhead architecture, the properties of the ink, its acoustic response, and its rheological response in these high shear geometries. And the chemistry that we can use is based on the geometry of the architecture in the driver. So some of the sample layouts we've got here from different manufacturers visualize how, when we apply these electrical fields in a printhead based on our drive electronic signals, either a digital or an analog form, a square form or a trapezoidal, we generate these temporary pressures. The architectures here allude to how the ink is delivered down into this nozzle stack, and pressures are managed. So the larger geometries allow you to recirculate at faster rate and push the viscosity bounds and the loading of the material into higher modes. And these squeeze modes heads may be, in this drawing an isolated wall, so the deflections just drive that nozzle, or they may be in a shared walled architecture where they deflect bidirectionally and actually jet into neighboring nozzles as well. So when we look at that in typical waveform shapes, we have a digital waveform in the top left where we're just switching, we're sending time lapse signals through our electronics based on whether we want to deposit material for a pixel or a voxel or not, and we can fire neighboring nozzles at the same time. In a cycle-driven and shared wall head, we have to complete firing cycles where we apply activation, ejection pulses and cancellation pulses, and we have to do that on neighboring walls before we can repeat fire the same nozzle. When we talk about analog waveforms, these are typically generated outside of the print head in the drive electronics. So we have amplifier chips that address the head on a row by row basis. But we can change the rate of change, the amplitude and the duration of these pulses independently to create these temporary pressure pulses, build them up in sequences, either to generate larger drops in a binary or addressable volume in binary, selectable, or in grayscale where we have mapping where we can fire a single or multiple pulse ejections to have addressability of volume so that we can play with these print regimes to manage deposition of material within our bed to achieve different physical properties. How do we typically try and refine this response from the electrical signal, the acoustic response to the fluid and the drop formation? It's typical to use a drop watcher. Meteor's developed our own system that coordinates the signals through our data path and manages power supplies to coordinate a droplet ejection with a stroboscope and camera system. So in an ideal world, we'll be jetting fluids that come out of the head, they detach from the nozzle, they form a nicely coalesced droplet, they track away through flight, and they're nice and spherical. In this case, by firing a strobe in 2 positions in its flight, we can get its directionality, its volume, its diameter, and its speed. In the real world, the things that we're constrained to formulate into our materials to make them jettable mean that we may be fighting a compromise between the physical property of the material in the part with how it jets, and therefore having to deal with having a ligament or satellite that may detract from the quality and resolution of the edge of a part. It may cause you to have a short circuit if you have a satellite drop landing somewhere where you don't expect it to in an electrical device. So by refining the electrical inputs to the print head and therefore the shape and timing of the pulses within, we can harness that acoustic response of the material specific to the geometry of the print head selected. So that's based on the solvent phase of the fluid, and the solid's loading will determine its acoustic response. And then the amplitude that we drive it at determines the speed of the ejection. So when we look at how we at the output of a droplet in flight, where we're overdriving a fluid and we're getting, in this case, this is just a 7 picoliter droplet. As we look at its evolution of flight, each of these ejections as a single event has a slightly different breakdown in that tail and satellite. So can we tolerate that in our print process? Can we manage it and refine it with our electrical signals or our how we profile our part in meteorite? Do we change the resolution to compromise? And then using grayscaling that Steve alluded to, enables us to address these range of deposition rates to achieve average dosages over an area. So ideally using combinations of pulse to have addressable drop volume. What that looks like when we start to characterize a droplet in flight is that we see our nozzle being driven, and each sub-ejection happens with a reasonable amount of timing, with difference in acoustic efficiency, so that those droplets are ejected, they come together, they coalesce in flight, they track away from the print head as a coalesced droplet that's with consistency, so that we can register that material from the print head timings and electronics and encoder timings of the machine into material on substrate at the right point in time. So we're constantly trying to, all of us that are presenting are improving our analysis. How are we formulating for inkjet in our blends of active reagents in the fluid? How does that jet? How does that print process build up in a powder bed, and with the mechatronics, with the drying and curing and sub processes? By improving the optics, we can clearer characterize the droplet in flight down to its volume in ligament and tail, volume in satellite, and the mist that may be generated that's not necessarily going to impact your build quality, but may impact your reliability of your system. How long can you print for before you start to have to do maintenance to recover missing, deviating nozzles that will be detrimental to your print process? We want these to be industrial manufacturing processes, so they have to be robust, consistent, and manageable. So all of these print optimization tools allow efficient evaluation of our inks, our different print heads on a modular architecture, how the waveform affects the deposition regimes and your build and your print steps, how managing formation and velocity affects dosage and viability of your manufacturing windows. So that's where the four of us presenting today and our individual tools and expertise come together to provide that that expert knowledge, that assistant, the tools, services, and training to help all of you that are interested in taking on inkjet and additive into manufacturing tools of the future that we want to help to market. So on that, I'll go back to Dennis to lead the Q&A session by Dendrite. And again, thank you to my co-presenters for the opportunity to talk.
Awesome. I'd like to kick it off by thanking our expert panel today. That was a wonderful presentation. We do have some questions in the chat. Again, just a quick reminder, if you do have any questions that you'd like to ask the panel, please feel free to drop them in the chat. We will address them now. Let's kick things off. Can you please elaborate on the topic when such binders will be available for actual use on binder jetting machines? I believe this is addressed to Dr. Black.
Yeah. Difficult one to answer that, because there's lots of, they're already existing on binder jet machines, so we can print them on existing binder jet machines. I think these would suit perfectly as well with Dan's B-jetting systems. It's ideal. They've been designed for that flexibility of material systems. I'm not sure whether the question means are they available for current desktop metal or X1 machines. I know that X1 have done nanoparticle binders. I don't know whether the person who asked the question wants to elaborate more on that. But they can certainly be used on existing jetting machines, binder jet machines.
Excellent. We'll see if we get an elaboration in the chat. In the meantime, let's move on to our next question. Does Dendrite support any color textures?
Right. So within the Dendrite software, we currently support image-based labeling, but do not currently support like a grayscale depth map. We are currently developing that feature, though.
Great, thank you. How was the meteorite file naming convention determined?
It's flexible. Obviously, it's configurable in the print engine. The default is color 1 cut to color N onwards, but it can be, you can rename that to map the output of your build processor. Whether it's material 1, binder 1, release agent 1, call it what you want, as long as you map the right section to the right plane in the print engine. It's agnostic to the name.
Yeah. And to build off of that further, within Meteorite, the naming convention is Meteor specified, so that's compatible with existing workflows.
Great. You've shown a lot of color output in Dendrite software. Is it also able to do grayscale?
Yes, within the Dendrite software, you are able to do grayscale. You could do monochrome output and then set the grayscale via the red channel.
Next one here, how does the electronics interface with machine tools?
So the Meteor print engine is taking an encoder input from the machine, so it knows the relative position of the print head over the powder array. So it would have a datum point at the start of travel. Each print head then has an XY coordinate inside the machine, and the data is then clocked to each nozzle appropriately based on the encoder inputs, and that works bidirectionally or in multiple paths with a single head where it's also doing Y steps.
Excellent, thank you. Our next question, what do you think the future of binder jet will look like?
Yeah, I'd like to lead that one off. I think that the first thing you're going to see is an explosion of OEMs, and I think you're already seeing it. I mean, I think that you're starting to see a lot of new machines come from various places all over the world, specializing in all kinds of different materials. So I think that's the first thing you're going to see is, similar to how we have 70, 100 laser powder bed manufacturers out there. I think you're going to start to see more and more binder jetting OEMs. And I also think you're going to start to see OEMs making their own custom one-off systems for exactly what they want to make.
Agree. And if I can add to that, Dan, I think the fact that we're now starting to see more materials development, we're going to start to see some quite crazy and unusual products being developed, because you're giving the artist the tools, a much wider palette of materials to process with. So I think we can only begin to imagine what might come out of that. But I think when we started at Liverpool and then through Meta Additive, I mean, a lot of the software to control those and even the heads to some extent were at the very early stages. Now we're starting to see much more open up of the software, and even thinking about the possibility of printing multi-materials. That's a different thought process. So I think it's quite an interesting time, but it's you've seen binder jet printing growing and growing. I think you'll see that trend keep on growing.
Do you think that there are any other key parts required for a successful jetting system?
Yeah, I think.
Yeah.
Sorry, Matt. I alluded to it on my last slide about characterization. I think that's going to become even more important because we're now starting to see more complex material systems, being able to manipulate microstructure. We need to be able to characterize those first of all to make sure that we've got what we thought we had. And a lot of the characterization facilities will also need a reimagining. You can't chop up whole components that have been printed in multi-materials because you kind of ruin the idea. Do they work together? What do the interfaces look like? So I think you'll also start to see the characterization guys get on board and developing new or modified material characterization systems that will lend themselves to additive manufacturing and binder jet. We can't wait, a month to make a TEM sample when actually you need to know in a couple of days whether you've got the material that you need, and creating that database of materials.
Yeah, as a system tool for developing inkjet processes, don't think about it too late in the day on your fluid delivery system. It's a microfluidic device that's doing the deposition. Again, quality of the management of bulk pressure and fluid delivery down to the print heads will cause you a lot of pain if you try and design that in afterwards or cheap out on it. So, yeah.
Yeah, and I'd just like to throw in there that, today we talked about the liquid side primarily, but those complicated recoders and all those different kinds of parameters and whatnot that you can design, those are an equally important part of the system. I mean, your substrate in any printing system and how you prepare your substrate is incredibly important.
Excellent. I like the collaboration. It really paints a picture for how vast this field really is. Next question we have in the chat, what droplet morphology is quote unquote best for inkjet? Material jetting, binder jetting, are they different?
Well, I can speak to binder jetting and say that, of course, as I say, substrate preparation here is incredibly important, and the condition of the surface of the powder is incredibly important. But in general, you want darts, what's been found over the years is that there's a minimum speed and shape that a droplet has to have when it hits the bed if it's going to penetrate. So, in general, you want something like a dart that just goes straight in.
But then I think, Dan, we've not even explored about how do functional binders penetrate into a powder bed. If you've got
Exactly.
Yeah, I mean, if you've got particles in there, you've got a dynamic permeability. How do they permeate through that powder bed? They're going to be different layer by layer. It changes the permeability of the powder bed when you put the binder in. So there's a whole lot of new learning to come out of it, I think.
Yeah, I agree.
Yeah, certainly
I
from
mean, the tools are getting better.
comparing binder jet to material jet, then the binder is supported by the powder bed. Or if we look at material jet, that's really pushing the viscosity ranges of inkjet, because that material has to be the finished part at the end. So that's where you have to get high molecular weights into it. You still have to be able to cure it thoroughly. You can't have it slump and the one layer run and slide off of the preceding one. So that's challenging the chemistry of it. Again, and that process window operations being opened up by advances in how to drive the head and supply the heads with these fluids.
Excellent. Our next question in the chat, how do I get a copy of Meteorite and how much does it cost?
Yeah, so Meteorite is actually free. You just need to get into contact with Meteor and they can provide you with a copy of the software.
Easy enough. Would you say that the jetting behavior of high viscous liquids, about 100 centipoise, is as reliable as that of low viscous materials?
It can be if you've tuned if it's well optimized, right? You have to have a good ink system, a good chemistry that matches the material's compatibility of the printhead. You have to be driving it in a sympathetic and tuned way. You can get any material to jet once. Getting it to do it exactly when you want it billions of times over is where it gets more complicated. Again, that's why the head manufacturers and Meteor all offer these technical services to do these waveform optimization processes with you, where we talk with rheologists and people in the other material science areas to characterize the material before you even put it in the printhead to find out whether it's going to jet reliably, because it has a shear profile during its life of being recirculated and pumped and activated that needs to manage that fixotropy and stability. There's no reason why 100 CP ink isn't going to be as jettable as a low viscosity ink. In fact, potentially more so, as it may be less volatile and subject to change.
Is there any bed packing or automatic layout?
So as Steve demonstrated via Dendrite's tools, there are a lot of nesting options available, either 2D or 3D, as well as lots of controls to set orientation, pack within constrained areas, avoiding other parts or avoiding keep out zones.
Excellent. I believe that does it for the questions in the chat. We'll give it another 30 seconds here to see if anything else trickles in. Any closing remarks from the panel while we wait?
I just think that, you know, we've got quite a hopeful future for BinderJet, but also not just for BinderJet. I think this webinar shows that to tackle manufacturing problems, it really is a holistic view. We need to create those manufacturing ecosystems to tackle challenges, and it's about creating value, not capturing value.
Excellent.
And I'd say if you are a budding OEM, I would say, you know, don't go it alone. I mean, while it's true that everything we talked about here today is all something you could in fact do yourself, you don't want to. You know, like there's no reason for you to go through all the pain of trying to put all these little pieces together when they're together already. You'll cut your design time like by years, you know, not by weeks or months, but by years. So my advice is to, you know, don't go it alone. There's strength in numbers.
Very true.
Excellent. Well, thank you to our expert panel. Thank you everyone for attending. And just a reminder, this is not the end of your conversation on jetting. This is just the beginning. So please keep an eye out for further communications from Dendrite, from any of the speakers today. We look forward to our relationship. And thank you all for joining. Have a great one.